Okay, good. So our second speaker today is Paolo Benincasa from the MPI in Munich, and he will talk about cosmological polytopes and non-dlog forms.
Okay, first of all, thanks a lot for the invitation to give to speak in this wonderful workshop. And actually, I thought to talk about this subject because I never gave a talk about this, and I thought that this workshop was the perfect environment to do it. What we have seen so far in the past days is that positive geometries have appeared in several contexts, for the description of several amplitudes for several types of theories, like the amplitude for any conformal mills, as well the momentum amplitude, the dissociated for by a joint phi cube. There are also like Stokes polytope for planar phi for amplitudes. Somehow it seems that these positive geometries might really have some fundamental role in the description of scattering processes. And also with the cosmological polytopes, they appeared for the description at least of some large class of toy models, which are typically they describe the wave function of the universe, the Bunch-Davies wave function of the universe in FRW cosmologies for conformally coupled scalar with the interaction of the type of phi to the k. And I will rely completely on Austin talk to all the background about what the wave function of the universe is. Here, I want just to remind that in this description of this wave function through Feynman diagrams, one thing that happens in the type of models I will refer to later is the fact that the dependence on the external data, that are this spatial momenta at the boundary, came not only through their moduli that with a little bit abuse of language we call energies, but also they will depend on the sum of these energies at each vertex. So I can label with x1 the sum of P1, the modulus of P1 up to the modulus of Pk, and with x2, the sum of the modulus of Pk plus 1 up to the modulus of Pn, and this y12 will be the energy of the internal state, which is just the modulus of the sum of all the energies which are on one of the vertices. Which means that I can forget about all this drawing considering these external states, and I can think about graphs of this type that sometimes we call reduced graphs. And from now on, when I will refer to the cosmological polytopes, I will think about, and when I will refer to a function of the universe, I will think about this type of graphs. Now, one thing that all these positive geometries have in common, irrespectively of the type of physics they are describing, is the fact that they have a unique canonical form associated to, which means that a positive geometry is defined by the fact that also their boundaries are lower dimension positive geometries. That translates on the fact that you have a canonical form attached to some specific positive geometry. This canonical form has just logarithmic singularities, or if you want, simple poles. And if you take the residue along any of these boundaries, so the residue of any of these simple poles, you get the canonical form which is attached to the geometry described at this boundary, which locally translate that another way to see it is that if you choose some local coordinates, you have this this structure where this W tilde is just some part which is analytic in the H equals 0 is what identifies the location of the boundary. In general, the canonical form is defined up to a constant, but which can fix if one declares that the canonical form attached to a point is plus or minus 1, which means that if you iterate this process of taking residue or residue or residue, what you have is just plus or minus 1 as a result. And this fix completely uniquely the canonical form. However, we also know that physical processes are not all described by functions which have simple poles.
Paolo, can I just step in here? Just very maybe it's a comment or a question.
Yes.
You still have two choices, right? Because it could be either plus or minus 1. You can always multiply by minus 1.
Well, plus or minus 1. That's typically it depends on the orientation.
Okay. Yes. Yeah. But yeah, if you think about this, yeah. So if you fix the orientation, then it's unique. Yeah. Thanks.
Yeah. That's very correct. Yeah. As I was saying before, in general, this function with just simple poles or with logarithmic singularities really describe a small corner of physical processes. And in general, you can have all other type of singularities. So a general question is how to associate non-dlog forms to a positive geometry, if there is a consistent way to do it. In this talk, I will be less ambitious. I won't make a general statement which will be valid for any positive geometry. I will focus on projective polytopes, and the cosmological polytope will be a specific example where things work in a beautiful way. And the idea is to try to make a systematics of how to associate non-dlog forms to projective polytopes. Now, also in this case, let's say we will be even less ambitious. That won't be completely general for any type of non-dlog forms. We will specify on those forms where poles can have, where you are still rational functions, but this rational function can have high order poles. Okay.
Sorry, Paolo.
Yes.
So when you consider non-dlog forms, you mean you want to see poles that are no longer just simple, higher order poles?
That's correct.
But what about those cases that the poles are all simple, but when you take it all the way down to 0 dimension, it's still some function. It's no longer, you can no longer fix it to be plus minus 1. For example, for like Yang-Mills, rather than phi join phi cube, where the singularity structure is the same, but in some sense, you know, it's not strictly speaking the dlog forms I mean, we're familiar with. It's the same singularity structure as tetrahedron and so on. I mean, have you thought about those cases in your?
No, no. This case won't enter.
Okay. So you are directly going for higher order poles when you say non-dlog form. Okay.
That's correct.
And also, Paolo, are you talking still about top forms or lower forms?
Not necessarily top forms.
Not necessarily top forms. Okay.
Okay. So let's start by introducing. This what I'm going to say now is all based on this work with Matteo Parisi, and let me introduce some extra definitions, starting with the one of covariant form. Now, in general, one of the characteristics of the canonical forms is the fact that they are GL1 invariant. So if you make a G1 transformation, they will stay invariant. Now, I will introduce when I talk about covariant forms, I'm thinking about a differential form. I indicate now this small apex K and P is the fact that is referred to a given polytope P in such a way that it is still a rational function with some numerator, and the numerator still is defined by give the boundaries of P, but the difference is that they have some extra power. And the defining feature of this expression will be simply that it has to have a definite scaling under a GL1 transformation. So if you rescale y by some lambda, it has to have to scale like lambda to the minus k with k positive. Okay, and then also a second requirement is that if you take the Laurent expansion, if you choose, for example, some local system of coordinates, you make a Laurent expansion around some boundary, the coefficient is still a covariant form with lower degree. This, if you set k equals 0, you will go back to the definition of the canonical form. So this is a straightforward generalization of what is a canonical form.
Can I ask a question? So in this last condition which you have there, so the h is defined in such a way that when h equals to 0, you're in the boundary, right? But you could change to a different coordinate system where you define h prime equals to 2h, say. This means that there's this omega in front would change in that case. So how do you choose how you parameterize the way you're approaching the boundary h equal to 0? And because in the dlog form, when you reparameterize the way you go to the boundary, say multiply by 2 your variables, then everything disappears because of the dlog. But in this case, it just changes the constant which you multiply the omega. So is the omega defined projectively, or?
That's okay. This is one of the big difference with this case and what you are accustomed to with the canonical form. So in general, exactly really because of this GL1 covariance, this this covariant form are not defined uniquely. So when you really talk about covariant forms, we are talking about a class of differential forms which are defined up to scale. What this means is that, contrary to what happened in the case of canonical form, where the equivalent requirement, the GL1 invariance and the fact that you take the residue, you have still a canonical form. That's set completely your canonical form. In this case, this requirement do not set uniquely the covariant form. Okay, so in this sense, this covariant form, given a polytope P, there is a variety of covariant form that you can attach to it.
But is it just projective? Should I think about this projectively, or there's something more which can happen? I mean, is it just rescaling by constant, or?
Yes, no, that's just rescaling by constant.
Okay, so they are defined up to rescaling. Yeah. Okay, thank you.
Yeah, that's correct.
Sure. Paolo, but maybe I can ask that question again. Just from Tomek's question, it would naively seem like you have a kind of a separate freedom on each boundary for what the sort of scaling would be, depending on whether you represent it as h or 2h, or it's not obvious that all those freedoms are captured by just this one overall scaling. Are you saying that the forms are indeed uniquely defined just up to this overall GL1 covariance?
No, I'm not saying that. I'm saying that exactly because what you just said, that you can you have a plethora of different covariant forms which will satisfy this for the same object.
Okay, so even apart from the GL1 covariance, that there's some sort of different representation in the neighborhood of every boundary somehow.
That's okay. Correct. That's totally correct.
Okay.
Okay, and that's actually is actually the consequence of this fact, because as I said, you approach this boundary, you have this which has the scaling, maybe to fix the constant to be some number, right. Then you to go another boundary, and then you have still the freedom to fix that constant.
Right. I see. Right.
Yeah, so in this sense, it's as what I said, that these covariant forms are not defined uniquely, which is a big difference between this case and the case of canonical forms. Right. Okay. So.
But still, the residues are not residues. The coefficients of these are a GL1 representative of the lower forms. Just that as we go on, we can get more and more. Yeah. Okay.
That's correct. That's totally correct. Okay, so here is this fact that these are not unique, and also from this fact that this if you fix what is the degree of covariance of this form, you can have a maximum powers of a maximum multiplicity for a given pole. Okay, so now. There is a second definition. Okay, so maybe this fact that these covariant forms are not defined uniquely is a little bit uncomfortable. But now let's move to somehow a refinement of this definition, which won't be any better in terms of uniqueness. And then I will get to a very systematic way of obtaining this type of forms. Now, in general, if I have some given polytope, I can have a sign triangulation of this polytope, which means that in terms of the canonical form is given by the sum of the canonical forms related to each of the collection of the polytopes, which sign triangulates the original polytope. Which also means that there are spurious poles which are related to the faces, which are faces of the PJs, but not faces of the original polytope. In this sense, we defined what we call a covariant pairing, which is the association between a given polytope and a differential form with some scaling k. In such a way that is given by a sum of covariant forms which are associated to a given collection of polytopes which triangulate the original polytope. So also in this case, again, you have to pick, when you define the sum, each time you have to pick some representative of the covariant forms, because as I said before, these are not defined uniquely, which means that also this covariant pairing are not defined uniquely. And there is a second feature that while here, in the case of canonical form, there are spurious poles which cancel upon summation. Here, the poles which are related to the faces of the PJs and that are not related to faces of P can be still there, but with a lower multiplicity. So if you like, this covariant form, this covariant pairing keeps track of the fact that you are associating a differential form to a particular sign triangulation of your polytope. Okay. Now, why this definition? Even if they are not unique, they associate not univocally some differential forms with some non-dlog forms to a polytope. Why these definitions are useful at all?
Sorry, Paolo, can I come back to the previous slide? Sorry, I think I haven't understood it. So are you saying that there's a way to extract these covariant forms from the triangulation?
More than extract, you are, this is again a definition, you are given a polytope which has some triangulation, you can associate another differential form to the polytope, which is related to, which is defined as a sum of covariant forms related to each of these of the component of the triangulations.
Okay, but this form, there will be many, many more than the freedom here is much bigger than the one which we discussed before, right? Because
Yes.
because you could fix the divergence at each spurious boundary to be 1, 2, 3, or degree up to k, right? So there's this family is much larger. Is that correct?
Yeah, well, the only requirement that you ask in definition is that yes, when you get when you sum over these covariant forms which share a face, the order of the multiple pole goes down. That's the only restriction. But you're right.
It doesn't have to be logarithmic. I mean, it doesn't have to be logarithmic. It can be also quadratic there.
That's correct. That's correct.
Okay.
That's correct. So, but you're definitely right. You keep having a lot of freedom, even more than before. And just to illustrate what I'm saying here is that, for example, you can take this point of P12, which is just a segment in P1 with boundary 1 and 2, and then you can sign triangulate it as considering the canonical form given by the sum of canonical form of the point of PT2 and the sign of and the canonical form of the point of PT1. Okay, with the right orientation. Okay, now, for example, I can associate this canonical this covariant form to the point of PP2 to the point of P31, which are of degree 1, of covariant degree 1, and they will give me, if I sum them, they will give me an object which has singularities along all the three boundaries. Okay. So, which is something that typically you don't have because this boundary tree in this case is completely spurious. It's not, it just you are triangulated something outside. Okay, so this is also this is one example. Another example. So in this sense, we say that while these two are covariant forms, this is a form which is in covariant pairing with this polytope. So we are attaching to it through this definition. Okay, so the same we can change.
Can I ask one more question? So here you're associating a form to a segment 1, 2, but yes, this depends on point 3 now. So
yeah, that's correct. That's correct, and because this cannot prescind on the fact that you are coming to it from the triangulation.
But how can you say that this is a function of a segment 1, 2 if the 3 is explicitly written there? So you're interesting, yeah. So it's something more than just 1, 2, right?
Yeah, I mean, because you are keeping track of the fact that you have a triangulation which is passing from an external point and a concrete external point.
What I'm saying is that this omega depends on the triangulation, not only on the polytope.
Yeah, depends on the triangulation of a given polytope. Yes, depends on the triangulation. That's correct. Okay, so and this is another example which is the same where I just change which one as multiplicity 2. Okay, so so far what I gave you is the definition of two ways of attaching differential forms with non-dlog forms to polytopes which are not unique. One has to keep into consideration specific triangulation, so don't look very satisfactory, neither systematic. How can we do this? How can we make sense of these differential forms in a more systematic way? So the point is there is an interesting thing that actually we can do to relate these definitions that I just outlined to actually something from which we are more comfortable, which are precisely the canonical form. So if you consider a polytope which is on facets, and we consider some hyperplane which intersect the polytope P, but doesn't contain any of the facets. Okay, so this hyperplane will never be one hyperplane of the facets. So so there is the requirement that this hyperplane has to intersect P. So this intersection will define another polytope. Will define a lower dimensional polytope. So if you compute the restriction of the original polytope onto this hyperplane, you get some other polytope. Now, you can define the what we call a covariant restriction of the canonical form of the original polytope. Is taking the leading the zero order Laurent coefficient of the differential form. What does it mean this? If I represent given that these hyperplanes are not facets, are not faces of my original polytope, the differential for the canonical form won't contain any pole along this hyperplane. So if I make some Laurent expansion along the direction of this some direction for this hyperplane, I will take the first order, which would be the zero order one. Okay, which another way to saying I can define this I can define some differential form by taking the integral along this hypersurface of the original canonical form divided by the conditions that define this hyperplane. Okay, if you do this, it turns out that this differential form that you get has a specific scaling. Namely, if this has codimension m, you'll get n minus m scaling under GL1. Then if this hyperplane intersects the facets, a certain number of facets, then the related pole will collapse to generate a single pole of higher multiplicity. And in general, can have poles outside this polytope pH. Okay, so let's see some example. So let's imagine some very simple example, a triangle in P2, and I take a line which passes through the vertex 1 and intersect the boundary given by the side 2, 3 in this point 4. If I take the definition, this is the canonical form related to the triangle. If I take the definition I gave you before of this other forms, you will get that you see when the polytope, which is the restriction of the triangle on this line, is just the segment 1, 4. But in this case, the boundary 1, 2 and 1, 3 of the triangle intersect the hyperplane H in the same point, which is the boundary 1. So these two poles will just collapse in the same to form will collapse to the same point given a higher order pole. And in this case of the square is the same. You have the hyperplane that in this case is intersecting both is intersecting the square into higher codimension boundaries, which are the vertices 4 and the vertices 2, and this will tell you, given that this boundaries where is intersecting the square has codimension 2, will give you the precisely double poles. Okay, this is a specific choice for the local coordinates. Now, in this case, what you get is a definition precisely of the what I call earlier a covariant form. But we can take other example. I can take again my square, and I can intersect. I can consider a line which pass through one of the vertices, but then intersect the facet 3, 4 outside the polytope. So in principle, the restriction of the square onto the line is still the segment 2, 5. Nevertheless, when you compute this covariant restriction on of the canonical form of the square onto the hyperplane H, we also know about this point 6. And if you think you think about this, you can think about this, and so you will get some result which has a pole in this point, which involves this point 6. But then you can think about this object as coming from having a sign triangulation of the square 1, 2, 3, 6 with the triangle 1, 6, 1, 6, 4. And you separate like this, you obtain precisely a sum of two covariant forms attached to these two polytopes, which sign triangulates the original one, which is precisely the definition of a covariant pairing that I gave you earlier. So the point is that when you start from a general polytope, you make a restriction of the canonical form along some hypersurface. You can know, or you will know also about where the upper surface is intersecting the facets of your polytope outside the polytope. And this is a more complicated example, but in line of principle is the same. You can think about the original polytope that I call P5, this pentagon, is coming from this sign triangulation, which is the square 1, 8, 4, 4, 6, the triangle 2, 3, 8, 8, 2, 1, and 6, 4, 5. Okay.
But coming back to Tomek's comment from before, yes. So the real object in these cases are not the intervals, your little red intervals. The real object is both a piece of information, the original polytope that you started with, as well as the sort of plane that you're intersecting. That's the, so you're not really associating a non-dlog form canonically to the lower object. You're associating a non-dlog form canonically to a pairing, higher object and the slicing plane.
Yeah,
I mean, after all, yeah.
You're definitely right that in this way the key information are the polytope you're starting with, and the hyperplane on which you intersect. That's totally correct.
I also have a question.
Yes.
Sorry, maybe something I don't see. So you have these two terms that you sum.
Yes.
But it looks to me like they have different weights, right? With respect to 562. Is this because I have Z0 tweed or?
No,
sorry.
No, the weight should be the same.
Okay. Because the 6 on the right, it appears 1/6, and on the left is 6 square. In a sense. And also in your previous, in the simple one, in the segment, the two terms, they looked like really, okay, it was really just the segment divided into the blue and the red. And it looked like you were summing two forms with different. Sorry, maybe
no. For example, in this case of the segment, yeah. The weights are. I'm not exclude that I made some typo. But
okay, no, because no, I'm just saying P32, omega 1 of P32 is different way than omega 1 P31. but you're summing them, right?
Yeah, no, I might have made a mistake here because, for example, this is the final answer that you get, and as you see, yes.
Okay, yeah, okay.
Are correct. I may have made some typo.
Okay, thanks. Okay, I was just confused.
Yeah, but yeah, sorry.
It's also here, probably, right?
Yeah.
6 and 5. Okay, it has to be the right way. Okay, good.
Sorry for that. Okay, so now this, if you like, the general idea, if you want to talk about non-dlog forms with higher order poles, is to make a restriction of the canonical form associated to a polytope along some hypersurface. That's the general idea. Now let's see this the realization of this idea on the cosmological polytope, because it's also what's behind the description, this combinatorial geometrical description of not only of propagating massless scalars, because typically the cosmological polytope describe the wave function of the universe for conformally coupled scalar. If in principle you want to have the possibility of describing a larger set of models, you have to worry about what's happened to the cases where you don't have canonical forms. And so all this construction that I described so far is what actually is behind the description of this wave function with propagating massless scalars, and as a beautiful polytope description. Before going to that, let me outline what's the standard definition of the cosmological polytopes as we define in the paper with Nima and Alex Poznikov. And probably a simple way to understand it, it's let's start from a graph which has the labels x1, x2 associated to the sides, and this label y12 associated to the edge. And then I can construct a space with local coordinate precisely these labels, and with this vector defining 3 points, which I will take to be midpoints of a triangle. So these 3 points at the end of the day define a triangle with vertices given by this combination of x1 minus y12 plus x2 and so on. Okay. So this is as a canonical form associated to it. If you compute it in this coordinate, the coefficient of the canonical form is precisely what gives you the wave function for the process associated to this graph. Okay. Now, if you want to go to study more general processes. There is also a way to keep track of the vertices by just associating a marking on this graph. For example, I can indicate this vertex with an open circle in the middle. This other vertex where x1, there is a sum between x1 and y12 with an open circle close to x1, and the same for the vertex where I have a sum between x2 and y12. Okay. So this is very important, because when we construct more complicated objects, then you won't be able to draw anymore, and this is a very useful way to keep track of the phase structure and vertex structure of the polytope. So, for example, if I take now a collection of these graphs, which means I have, for example, 2 triangles, each of which is associated to one of these graphs. Then, for example, I can combine to this graph to give me this 3-side graph, or this 1-loop 2-side graph, which from a geometrical point of view boils down to defining a space with here are 5 local variables, so P4 in this case with 4 local variables, then P3. And then in this case, intersecting these 2 triangles just in the middle, in the midpoint of in the midpoints of one of their edges, and in this case, in the midpoints of 2 of the edges. So if I take the convex hull, they define some other polytopes, and again the canonical coefficient of the canonical form is what gives you the wave function related to this graph. Always recall that you have some external lines associated to these sides. Okay. Now, again, for example, these are easy to draw. If I already have these graphs, it will be just impossible to draw and staring at the object and try to guess what are its properties. However, there is a nice correspondence between the facets, which means the residues of the wave function, and the subgraphs of these graphs, which means that one facet corresponds to a given subgraph. For example, if I take the subgraph, which is the graph itself, this is associate. What you do is when you take this subgraph, you associate to it the sum of all the external energies, which are given by the energies in this case associated to these vertices. And so you know that when you take this subgraph, it is related to the limit for which all the sum of this axis is going to 0, which is precisely when the total energies are going to 0. So this corresponds to the scattering facet. And then also there is the general rules is that when your subgraph include an edge, the vertices which do not belong at this facet are the vertices which I labeled with the open marking in the middle. In this case, I'm with this axis, I'm just identifying all the vertices which are not there. Instead, if I take some other subgraph which is crossing, which is cutting some edge, you don't have to include the vertices which are closer to the sides where you're cutting the edge. So this marking tells you which vertices do not belong to this facet, and so if you take the complementary notation, which is the first one, you know directly by considering the subgraph which vertices of the polytope characterize this given this facet. Okay, so now, this is what is important to know about the cosmological polytopes for what follows. Now, let's see how we can make any association of this construction to what I said before about the definition of these non-dlog forms. I can generalize this construction by not only considering these two-side graphs as building blocks for constructing more complicated graphs, but also, and therefore just thinking about the cosmological polytope as coming from intersecting triangles, but also I can consider tadpoles, and the graph associated to this tadpole is just a segment. Okay, for example, if I intersect this graph with this tadpole in this way, so I'm identifying this x2 with this x. What you're doing is intersecting this triangle in this midpoint with this segment, this other midpoint, and what you obtain is simply a square pyramid. Okay. Now, if I choose a hyperplane.
Sorry, Paolo, that was a little fast for me. Can you explain this example? Who are we intersecting with who?
So I'm taking this. I'm taking from a graph point of view. I'm taking this two-side graph, and I'm intersecting it, identifying for x2 with this x. I'm merging these two graphs together, okay, by saying that x2 and x are the same. So
so we get the square at the bottom there. Then I see. Okay.
That's correct.
Yeah.
Which means that I'm saying that the sum of this vertex with this other one
right.
give the sum of these two.
Right. Okay.
Sorry, this is an H2.
But yeah, I just got confused because I thought you're right. You're identifying the midpoint of your bubble with one of the midpoints of the triangle, and that's where you're getting the square. Okay.
That's totally correct. Okay. So now, if I take the hyperplane, which is identified by the equation that H2 is equal to 0, which will be the hyperplane which precisely contains this triangle, what I obtain is that this hyperplane intersects this pyramid just inside the pyramid, no outside, and precisely on the triangle which is associated to this to this graph. Okay. So now, if I consider now the canonical form which is related to this pyramid, and I consider the covariant restriction undefined earlier on this hyperplane, I will obtain a differential form with a higher order poles associated to this triangle. Because now really it's not like in the case of the covariant pairing that you get also intersections outside. In this case, in the cosmological, in this case, or in this polytope case, what you're getting is just boundaries along the boundaries of this little graph. Okay. So another way, this is generally a way to count the expected multiplicity of the poles that you're gonna get is that is given by the codimensionality of the if, for example, this hyperplane is intersecting the pyramid in a higher codimension phase. So in this case, it's intersecting. In this case, in this line. In this case, in this other segment. So it's intersecting in codimension 2 boundaries. So what you will expect that the resulting covariant form has double pole precisely along these two boundaries of this triangle. One thing that happens is that if you take this pyramid and you can write it as in a triangulation which will correspond graphically to this formula. What all this is doing is that when you take the restriction for H2 going to 0, what you get is that the canonical coefficient of my covariant form is nothing but a derivative of the canonical form of the triangle. Okay. So in general, in the case of physical interest, where I was claiming that this type of construction can describe a propagating scalar, what you can do is that you can consider it as a building block, not just this segment, these two-side graphs, and then join them together, but you can consider a collection of graphs where you attach two tadpoles, one for each site, to the original two-side graphs. So, for example, you have 3 of them, so you can construct a bunch of other graphs, 3-level, with different topologies. And then when you do this, and then there is a natural way in which you can define the hyperplane which intersects this, where to do this restriction, which is precisely identified by setting by setting all the labels which are related to this to these loops, to these tadpoles, to 0. Okay, so and that guarantees you that you're gonna get a differential form with a higher order poles, which is associated to the graph that you obtains by just eliminating these tadpoles. So in this case, all the rules that I told you before about facets identified by a subgraph still hold. So all the studies that you can make about the phase structure, the facet structure of the cosmological polytope, you can do it here as well. And upon the restriction, all the feature of the new of the differential form that you get associated to the lower dimensional polytope are completely inherited by the structure of the bigger polytope.
Paolo, if I wanted to start from the graph without this rule of how I get it from gluing together basic building blocks, if I just want to start from the graph and then uplift by adding these little bubbles, I just have to add whatever the degree of the vertex is, number of bubbles to every vertex. Is that right? Is that
that's correct? That's totally correct.
And then so that uplifts to this higher dimensional object, and then you just get rid of all those bubbles by setting them all to by going to the hyperplane where you set them all to 0, so you come back to the original set of variables. But now you have forms with higher poles.
That's correct.
And the claim is that that's what just on the nose gives you the massless wave function.
Yeah, that gives you on the nose the massless wave function. If you do it in this way, that for each segment you have 2 bubbles attached. For example, here there are 3 segments, and for example, there is this tadpole which is associated to this site, and then
that's what I meant. If I started from the bubble to begin with, the rule would be that for every vertex, I add the number of bubbles given by the degree of that vertex.
Yes. Okay.
And if we do that, and then you start from that canonical form, eliminate, you on the nose get the massless scale. Wow.
That's correct. That's correct. Okay. So
sorry.
Yes.
Sorry, related to this, maybe it's I don't understand. So does it correspond to something physical, removing a bubble or adding a bubble?
Removing
some limit, physical limit.
Physical, you mean geometrical or really of physics?
Physics.
Now, if you think about it, all the labels that I attach to this edge have the meaning of energies associated to the momentum which is propagating. Now, in a tadpole, here really you shouldn't put any label, because here, because of conservation of momenta, here the loop is going to be 0.
Mm-hmm.
So if you like, the fact what allows me to uplift, to attach this bubble and attach to it a polytope is precisely the fact that I'm saying that there is an extra label associated to this edge that is not there, which means that I'm ignoring momentum conservation on the tadpole. So getting rid of the tadpole means, setting this h to 0 means that you are going eliminating this tadpole. You mean that you go into a configuration where you have all this momentum conservation all well preserved and all well defined.
Okay, thanks.
So a nice thing of this, as I emphasized in the very simple example when I was considering just a two-side graph with a tadpole associated, the attaching a tadpole from a mathematical point of view also means that you are taking the canonical function associated to the graph without tadpoles and apply a derivative operator with respect to the label associated to the site. Okay, so in a generic way, when you take the canonical form or associated to this graph with tadpoles, you take the restriction. The canonical form of the canonical function, the final canonical function, is nothing but product of derivatives of the canonical function associated to the graph without tuples. Okay, and this can happen in an iterative way, because you can add iteratively these tuples, and you can always write, and this is indeed true, and iteratively it's true for any type of graph, that you have a sort of wave equation that the canonical function has to obey, where this omega hat is the resulting canonical function, which in general has to be positive. So this is a very curious fact that I think deserves some extra thought. Okay, so when we do this procedure, so we get a canonical covariant form which has poles along the boundaries of the restricted polytope with a higher multiplicity if H intersect P in higher codimension phases. So it's important also, one thing that is important to keep in mind is that in a naive way, when we analyze, for example, let's say that I'm interested in knowing the power of the total energy pole that I will get after doing this restriction. One thing that I could do is that I know that in the final, when I get rid of the start poles, this graph, the phase of the scattering facet related to this graph is going to be given by those vertices excluding these two. Now one can think, okay, let me look at all the facets of this guy, which also contain this object, this structure, which are, for example, these four. So naively one will think, okay, when I get rid of this tuple, then all these four singularities will collapse and will give me a degree 4. So it will tell me that the multiplicity of my total energy pole has to be 4. This is incorrect because when you have to be sure that really there is an intersection, an existing intersection between these four facets. And what's happened is that, in quotation mark, the intersection among these facets also intersect the locus of the zeros of the canonical form of this object. So really, there is no place. So you don't have any contribution for. The power of this the actual intersection between these facets is of codimension 3, not 4. So, and this means that what you expect, or say another way, you have to make sure that the facets that what's the dimensionality of the space where these facets intersect. And the point is that the codimension of where these facets intersects, the facet identified by these vertices, is 3. So what you expect is effectively is that the degree of the total energy pole, the multiplicity of the total energy pole related to this graph is 3. Okay. So let me wrap up. So there is a way to associate projective polytopes to differential forms with a higher order pole. We had to define this concept of covariant forms and covariant pairing, which somehow associate forms with scaling and with the higher order poles, either to polytope, like in the case of covariant forms, or to triangulation of a polytope in the case of covariant pairing, which are in both cases not defined uniquely. But there is a way to consistently obtain them, which is starting from a higher dimensional polytope and computing the restriction of the canonical form of this polytope along an hyperplane that you can choose. Now, if you don't have any other direction, in principle, also here there is ambiguity because there is no natural way in which you can define this hyperplane. You can take the hyperplane you like and do these computations. However, in the case of the cosmological polytope, there is a concrete way to implement these ideas, and there is a natural way to identify these hyperplanes, which are given by those planes defined by the equation which substantially will eliminate the tadpoles that you had to define this higher dimensional object. So what is nice of the last bit is that the fact that this object describes and gives you all the characteristics of a propagating massless scalar of the wave function for propagating massless scalar. A little bit gave the direction of how the construction had to be, but it has a graphical interpretation. There is, as I said before, a natural choice for the hyperplane nowhere to restrict. And then you get a covariant form, which is naturally attached to the graph that you obtain just eliminating the tadpoles. So now natural question is if there is a way to generalize this type of ideas, either to obtain, because another fact is that in this way, substantially adding this tadpoles to the graph, what you are doing is producing higher order poles because you're applying a derivative operator to the canonical function associated to the graph without tadpoles. A question is if one can escape this structure, can do a little bit a definition which is a little bit more general, a procedure which is a little bit more general, and also if these ideas could be generalized beyond the projective polytopes. And I can stop here.
Great. Thank you, Paolo, for this very interesting talk. Other questions? I actually have one or maybe two. Let's see also. So when you say the generalization to other operators than simple derivatives, so higher derivatives.
No.
So what would you
which operator I have in mind?
First, and then what do you expect to be related to in physics? So because so if I understand here, this that you did is related to the propagating massless scalar, right? Okay. And so what do you expect? Which kind of?
Very good. In the paper where first part of these ideas appeared, one thing that I found is that there is a recursion relation which associate which allows you to extract the wave function related to propagating scalar with some certain masses from the wave function for conformally coupled scalar. And you can write this recursion relation in terms of a differential operator. In the case of the massless scalar, this differential operator dramatically simplifies in being just a number of the derivatives that you have to apply. But there is, if you go to other, if you change mass, if you give, if you change mass, then the operator is different. So it has another piece from which so far I didn't find an interpretation. So I couldn't find a geometrical way of interpreting the recursion relation for arbitrary masses included in this in the validity of the recursion relation. So that is what I have in mind in the first place. Mm-hmm. And I guess with this I should answer both questions, because that's also the physical reason behind looking for other type of operators.
Okay, thanks. And let me also ask the other question. You are talking here about cosmological polytopes, but for all projective polytopes, this is valid.
Yes,
In sense that it's more general.
In general, these definitions are completely blind to the cosmological polytope. However, what is peculiar of the cosmological polytope is this realization in terms of graphs, and so how you can study the phase structure and how you can implement the restriction of the hyperplane, and what suggests you which hyperplane that there are preferred hyperplanes. In general, if you give me a polytope out of the box with no physical interpretation attached, I have no reason for choosing except my personal taste of choosing one hyperplane or another, and it's not clear that you can find also some graph interpretation. So that's the main distinction.
Okay, thanks. Great. Yeah. Other questions?
It seems like the sort of, I mean, yeah, you can take any polytope, any hyperplane, talk about the restriction. That's perfectly fine.
Yes.
What seems interesting is for the cosmological polytope, there's a natural set of hyperplanes for which the restriction turns into derivatives on the that's the connection somehow. That
that's correct.
and that the fact that it can be described in such a beautiful way by adding these little bubbles is a sort of cherry on top. But that's I mean, if you gave me a stick-like polytope and said, you know, is there a hyperplane for which I can intersect it? Can I grow it? So somehow you've got to take the polytope, lift it to higher dimensions in some way, and then get rid of it in order for that to turn into the derivative, right? That's what happened in your examples. Do we know? I don't know if we know, but I certainly don't want to do it off the top of my head at all. How would we take a cyclic polytope or something and sort of lift it to one higher dimension and then sort of project it back down in order to turn into a derivative? That's what's not obvious. But somehow that's the thing that comes for free from this connection with the graphs and the cosmological polytopes. That's the remarkable thing.
Yes.
Yeah. Can I ask another question? So the actual massless scalar is the operators like, you know, 1 minus kddk or 1 plus kddk or something like that, right?
Mm-hmm.
I mean, it's not just kddk. It's like 1 plus. Right? I mean, because the actual wave function is e to the ik eta for the conformally coupled scalar, and it's like 1 minus ik eta times, yeah.
That's correct. But here, what I'm considering that probably I didn't make it clear enough is that here the expression that you get is that the internal state is a massless, but the external one are still conformally coupled. So if you want to obtain the conformally coupled also in the external one, you have to apply.
Oh, I see. So it's only the internal ones still that are okay. So on top of everything, we'd have to do a 1 minus kddk on the outside. But you say that then just doing this, just on the nose with nothing else, is giving you the massless internal scalars.
That's correct.
I see. That's really interesting. I see.
Yeah. Otherwise, you're right. I mean, if you want to everything which is
no, I thought you would then it would just be a matter of adding any number of bubbles up to this maximum number, because that would be summing the kddk as well as the 1 parts, all of them together. But you say that just doing what you did just makes all the internal guys massless.
That's correct. That's correct.
Thank you.